Hello everyone. Today we're going to talk about the continuous time signal analysis using the Fourier transform. And just to give you the big picture, if you have a continuous signal that looks like this, and let's call this signal x of t, and you want to know what are the Fourier transform or what are the frequency content of this signal, and this signal is not periodic, so it may have infinite possible of frequency component like 0.111 hertz, 0.00001 hertz, and 1000 hertz. So we cannot use the Fourier series analysis in this case. Why do we want to know the frequency content? Because we want to do certain processing. Maybe we want to amplify certain frequency component, attenuate certain frequency component, and so forth. If I know what are the important frequency content in the vowel O, A, E, or sh consonants, then I can create a machine that will read a text for blind people. And there are many other applications for Fourier transform. So basically, Fourier transform is a mathematical equation that will take a continuous signal, not periodic, and give you the frequency content of the signal. The definition of Fourier transform is the following: x of omega equal the integral of the signal x of t e minus j omega t dt from minus infinity to infinity. If you want to know what that integral means, that means the following. If I want to know if 1 hertz is present in this signal, this you can think of it as a sinusoidal of omega 1 radians per second and phase shift 0. So I will multiply this by this signal. So I multiply x of t with this sinusoidal. That's the multiplication. Then I integrate, and that will tell me how much of 1 hertz present or 1 radians per second present in the signal. If I want to know a different frequency component, then I multiply x of t by this different frequency component, and they integrate and they get another value. So then x of omega will be like a function that shows the frequency content present in the continuous time signal x of t. And when I plot the magnitudes of x of omega, it may look something like this, and that is omega, and this is the magnitude. So it probably tell me I have a peak at this frequency, another peak at this frequency, and so forth, and large DC component. And if you wonder how do they do it in discrete, or how does the computer, like the processor or even MATLAB, how does it do it? How does it do the Fourier transform? Very simple. It's exactly stem from this integral. If that is your signal x of t, that you want to know what are the frequency content present in it, they take only samples. So they sample this continuous signal, maybe 1 million sample per second or 1,000 sample per second. It depends on your signal. Then if they want to know if 100 hertz is present in this signal, so they multiply by 100 hertz sinusoidal. But it's not. It's also only samples of these 100. And so forth. So now instead of the integral and this multiplication, what they do, this multiplication, they multiply sample by sample. So they multiply this sample by this and this sample by this and so forth. So they multiply sample by sample. Integration is a summation. Then they sum the product of corresponding samples. And if you have a value, that will tell you how big is this frequency. You will get a number, and that x of omega usually is a complex. It tells you the amplitude, and the phase it tells you did it start here or start here or here and here, and that's the Fourier transform. So let's start now to look the relationship between Fourier transform and Fourier series we learned in earlier chapter. Fourier series deal with periodic signal. So you have this periodic signal, and the period is t0. And we learned that we can represent any periodic signal as a linear sum of exponential. I can express this exponential in terms of cosine with amplitude, which is the magnitude of dn, and the phase shift, which is the phase of this dn. And how do we find this dn for different harmonic? We learned it is this integral. So that's what we learned in the Fourier series chapter. Now imagine the following. If we make this period t0 very, very, very large, we keep tau the same. That means that pulse will be way down here. And this pulse, because t0 is large, will be way down there. And for the system, really, or even for human hearing or something, that periodic signal now will look something like this. Just imagine if that pulse is 1 millisecond or 1 microsecond, and t0 I make it 1 hour. That means you have to wait 1 hour until this pulse comes. So again, it just looks like this. So it will look like a periodic signal. And this is the relationship between Fourier series and Fourier transform. You just let t0 goes to infinity. And then x of t0, this periodic signal, will become x of t, this aperiodic signal. And this integral here, dn, if you make t0 large, the period goes to infinity, then let's see what happened to omega 0. That would be 2 pi over t0. So if t0 become large, omega 0 will become very, very small. And then n just keep going to infinity. So n omega 0 gonna look like a continuous spectrum. It's not any more harmonic, because omega 0 could be, if t0 is large, omega 0 could be like 0.00001. The next harmonic 0.00002. So really, n omega 0 become a continuous spectrum or continuous frequency omega. So x of t0, because of this, will become x of t. N omega 0 will be a continuous, so that will be here. t0 over 2 here, t0 goes to infinity, so that will be minus infinity. Here will be positive infinity. Now, this term disappeared from this equation. Why? Usually, we have this t0 for periodic signal to average the different frequency component by dividing by the period t0. But for a continuous, you don't have to average. The signal does not go for a long, so we don't average it in the definition of x of omega 0. So we don't include this term here. So if I compare this integral to this one, n omega 0 just become omega. And that's the relationship between Fourier series and x of omega. Here, it will be dn discrete frequency component harmonics. Here, x of omega is continuous frequency. And usually, it will be complex. It has a magnitude and it has a phase. Let's look at this one. So this periodic we calculated in the Fourier series chapter dn, and we found dn this one. Later on, we will calculate the Fourier transform of this pulse, and we will find x of omega is this sinc function. If I compare this sinc function here to this one, this does not have the t1 over t0. For Fourier transform, it's not periodic, signal always end quick, so t0 we don't include it. N omega 0, we said it will become a continuous spectrum, so that will be just omega. And tau here is here, and A2 is 2. So for this periodic signal, it has harmonic, so it has the DC, first harmonic, second harmonic, third, fourth, and so forth. The Fourier transform of this aperiodic, it's a continuous spectrum. It has all frequency component. Now, if we move from here to here, we make t0 large. So that means omega 0 over 2 pi t0 will be very small. If I don't make it infinity, but just I make t0 large enough. So now the fundamental frequency, instead of 100 hertz, will be 1 hertz. So that means this line here now will be here and another here, because the fundamental frequency become very, very small. And suddenly these start looking like this. And that's the relationship between Fourier transform and Fourier series. When we have a periodic signal x of t, we calculate the Fourier transform by carrying out this integral. And after we calculate x of omega, we will discover it has a magnitude, and we call this the amplitude or the magnitude spectrum. And it has phase, and we call this the spectrum phase. And you will always find when you plot this x of omega, it will always be even, just like dn. The exponential Fourier series coefficient always even, and the phase always odd. The same thing. This is going to be always odd, and the magnitude here will be always even. Let's say you take x of t, you find its spectrum, x of omega, you process that spectrum, enhance frequency, delete frequency, eliminate, and so forth. How do you convert then a signal in the Fourier transform back to its time domain, so I can hear it, I can see it, it can make sense to me? Because in the frequency we are not hearing frequency domain, we are used to the time domain. Or an image, we are used to the spatial domain, not the frequency domain. If I show you an image in the Fourier transform or the frequency domain, it will make no sense to you. You have to see it in spatial domain. Same thing, speech. So how do I get from here back to x of t? Call this the inverse Fourier transform, just like we did for the Laplace transform, the inverse Laplace transform. And this is the definition. So you take x of omega, you multiply it by ej omega t, and integrate, and you will get back the signal x of t. And we can actually, in the Laplace, we don't carry out the inverse Laplace transform because it's a contour integral. We used to do partial fraction expansion, then we use the table. But for the Fourier transform, it's easy to carry out this integration to find x of t. Let's practice with some examples. We have a signal, x of t is this, and we want to find the Fourier transform. If I plot this signal, it looks something like this. So to find the Fourier transform, the definition says x of omega equal the integral from minus infinity to infinity x of t e minus j omega t dt. So the signal exists only from 0 to infinity, so that's the integral from 0 to infinity, and the signal equal e minus at times the exponential. And this will be 0 to infinity e minus a plus j omega t. So I add this and this dt. And if I integrate this, that will be 1 over minus a plus j omega e minus a plus j omega t. And evaluate t from 0 to infinity. This will be 1 minus a plus j omega e minus a plus j omega time infinity minus e minus a plus j omega times 0. And this will be 1 minus a plus j omega. Now this will go to 0 as long as a larger than 0. Because if a is negative number, negative 2 times negative, positive, positive times infinity, positive infinity, and this go to infinity, and the integral does not exist. So for this integral to exist, a has to be larger than 0. So this goes to 0 when a larger than 0. And this will go to 1. So that will be 0 minus 1 as long as a larger than 0. So x of omega equal minus here time minus, it become positive, and I get 1 over a plus j omega for a larger than 0. That's the condition, which makes sense. If a is negative 2, then this will be positive 2 times t, and positive 2 times t. As t go larger, these will go to infinity, and that integral will not exist. So this condition is important. Now, if I want to find the magnitude of x of omega, so I need to find the magnitude. In the numerator, it's 1. In the denominator, it will be a squared plus omega squared. And if I want to find the phase. One is 0 angle. The denominator will be minus tan inverse the imaginary divided by the real. And if I plot the magnitude, it will be as omega increase, x of omega, the magnitude will go to 0. When omega is 0, this is 1 over a. So it's going to look something like this. And this is omega. If you plot the phase, it will look something like this. When omega become infinity, tan inverse infinity become 90 degrees. So it's going to look something, and that's then time minus minus. So it's going to look something like this. And this here minus pi over 2, and this is positive pi over 2. Okay, and that's how we find the Fourier transform. So this signal, basically, this signal has low frequency, and as the frequency increase, it goes to 0. Now, just to show you the link between Fourier transform and Laplace transform, this is the definition of Laplace. So if I replace S by j omega, I get the Fourier transform. What does that mean? It means S here, the complex, as we said before, can be anywhere in this S plane. For the Fourier transform, it's only in the j omega. So x of omega has the strength of signals that has frequency in the x-axis j omega. That means here, sinusoidal. But the Laplace S can be somewhere here. So that means it's sinusoidal with decay. And that's the difference between Laplace and the Fourier transform. And if I give you the same signal here, we did that in the Laplace transform chapter, you use this definition. And that's what we got. And that was the Laplace transform. And the region of convergence, the real of S larger than minus a. That's the region of convergence. And as long as the region of convergence include these imaginary axis j omega, then this signal will have a Fourier transform. And if we replace S by j omega, we will get h of j omega, the same thing we did in the previous slide. If you compare this one to this one here, it's just here j omega, in the Laplace it's S. Alright, let's take some useful function that is used in engineering application. The first one is, we call it the unit gate function, with just a pulse that exists over tau second. That tau second could be 1 nanosecond, 1 picosecond. And we represent these by a rectangular. X will be the variable here. It could be time or space divided by tau, which is the width of the pulse. So it starts from minus tau over 2 to tau over 2. And at that discontinuity here, usually the signal will be the average, which is half. The unit triangle function, and we will see some application we use this rectangular and delta function or unit triangular function. It's a delta x over tau. Tau is the width here, that's the tau, and the amplitude is 1. And that line segment is defined here when x positive, and this line segment here is also here. And when x is minus, you will get this one. Plug for x tau over 2, you will get the 0. Plus for x minus tau over 2, in this equation, you will get 0. Plus for x 0, you will get 1, which is this. The next important function is the sinc function, or sometimes they call it interpolation function. They call it interpolation because if you have a signal like this and you have samples of the signal, a linear interpolation, you will just connect lines between them, and that's in linear interpolation. But if we use a sinc interpolation, which is more powerful, at that amplitude, a sinc function here, at this amplitude, a sinc function here, a sinc here, a sinc here. And if I add all these sinc components, I will get perfectly the original signal with no approximation, and that's why they call it the interpolation. Now, the mathematical definition of the sinc function is just sine x divided by x. And when you plug for x0 and x0, you get 0 over 0 undefined. You use L'Hopital's rules. This sine x become cosine x derivative, and this is 1. And you plug for cosine x, plug for x0, it will be 1 divided by 1. So the sinc function equal 1 for x0. When x0, it's equal 1. When x here or here equal pi, 2 pi, 3 pi, we know the sine pi, sine 2 pi, sine 3 pi is 0. So that is 0 pi here, here, here. And for any other value of x, that gonna looks like this. And it just decay to 0 as x become larger. And it's very important later on when x is like a complex function and you need to find the first 0. Always set the argument of x, sinc x, which is the same as the argument of sine, to equal either pi, will give you the first intersection, or 2 pi, the second intersection, and solve for the variable, whatever the variable. It could be space x, or time t, or frequency. Another example, let's find the Fourier transform, the magnitude and the phase of this rectangular function. We will use the definition, so x of omega. And if I plot this rectangular function, it looks like this, from tau over 2 to minus tau over 2, and the amplitude here is 1. And if I integrate, so the signal x of t only exists from minus tau over 2 to tau over 2. And it's equal in this range 1. E minus j omega t dt. And when I integrate this, I should get 1 over minus j omega E minus j omega t evaluated from minus tau over 2 to tau over 2. And this equal 1 over minus j omega E minus plug for t tau over 2 and minus tau over 2. And you get this. And this will be 1 over omega, or let me write it here. So the minus j, I'm going to multiply it here and here. So I will get 1 over omega ej omega tau over 2 minus e minus j omega tau over 2, and the j is here. So I multiplied minus j times this. The minus will make this minus plus, and the j will come here. I want to convert this to a sine function. So I'm going to multiply here by 2, and I multiply here by 2. And this will be 2 over omega sine omega tau over 2. And that's the answer. The x of omega of a rectangular pulse is a sinc function. So what I can do, I can manipulate this sine omega tau over 2. This omega here will come here. Inside, the argument of the sine function is omega over 2. So I will bring this 2 to be omega over 2. So that's, so far this is exactly the same as this. I need tau here. So I can multiply tau here, and I have to multiply tau here because I don't want to change. I want to keep it the same. If you divide by tau, multiply by tau. Now this function equal tau sinc omega tau over 2. And if I want to plot that sinc function, it's gonna look like this. The amplitude here, the sinc here, when omega, this is omega. When omega is 0, sinc 0, we said is 1. Time tau, that's tau. Now the first 0 here, how do we find it? We set the argument of the sinc to pi. That will be the first 0. So omega tau over 2 equal pi, and solve for omega, and that is omega will be 2 pi over tau. And that's the first 0. 2 pi over tau. There is very important concept here. When tau get larger, this is the main loop. All frequency in this main loop has good amplitude. Frequency after this main loop become quickly 0. I may draw it a little bit large, but it quickly goes to 0. So for function, usually they consider those are the important frequency, and they can delete these out. Look at the impact of tau. When tau is large, this becomes very small. That means the loop, the main loop, become very small, maybe from here to here. That means low frequency content. But let's look at the time domain. What does it mean? When tau is large, that pulse become large, which makes sense because if the pulse is narrow, then its change will be quick. So it's gonna change. If I make tau very small, this is very rapid change and quick, from 0 to 1 back to 0. So it has more frequency content this in comparison to this. So for this tau here, very small, this whole thing here will be large, and this will look something like this. Versus this one will look something like this. So a pulse of a small width will have high frequency, and that's why in communication, when you transmit a signal million bit per second or 5 million bit per second, to transmit 5 million bit per second, that means the pulse width should be very small, so you can squeeze 5 million of them in 1 second. If the width is small in time domain, that means the frequency content is large. That means you need a very large channel bandwidth to transmit 5 million pulse. That means when you go to your cellular phone carrier, if you want a larger data, they charge you more because you will have a larger channel to transmit huge data. Let's take these two more examples. We need to find the Fourier transform of this impulse. Then it will be x of omega. What do you expect it to be? Just an impulse like this. Well, we said if I have a pulse with tau very small, it will have large frequency content. So that one, even smaller, the pulse width. I can think of it as a pulse with a very small width. That means I expect these to have large frequency content, even though in time domain, it's just a pulse that happened in nano or picosecond. But let's calculate x of omega and see what will happen. So that means it's the pulse, x of t, which is the impulse, delta t, e minus j omega t dt, from minus infinity to infinity. And this one will be the integral. An impulse multiplied by any function give you the impulse and the value of the function or the sample at the location of the impulse. This impulse located at t equals 0. So plug for t0 here, e to the power of 0 is 1. And we learned the integral of an impulse is 1. What does that mean? X of omega is 1. If I plot it, that's the frequency time content, and it's just like this. That means that impulse little thing here has all frequency content. And that's why they use the impulse to find the impulse response of the system h of t. Because that impulse has all frequency content, so you will know how the system responds to all kinds of frequencies that is present here. Now, if I want to find the inverse Fourier transform of an impulse, now you are in the frequency domain. Now here is omega, and you have an impulse here, which means what? Whatever x of t that has this Fourier transform, it has only a frequency 0. So I should expect a DC. So let's find the inverse Fourier transform. So the inverse Fourier transform is x of t equal 1 over 2 pi x of omega, that's the definition, e j omega t. Remember, I am in the frequency domain, so that's d omega. So that will be 1 over 2 pi minus infinity to infinity. X of omega is this impulse, d omega. You will get an impulse at omega equals 0, multiply by this function, plug for omega here 0, and you should get e to the power of 0. So I will get the impulse back again, and if I plug for omega 0, I get e to the power of 0 is 1 d omega, and the integral of an impulse is 1. So the answer is 1 over 2 pi. So that's it. The signal x of t is 1 over 2 pi. If I plot it, this is time, it's just a DC of a strength 1 over 2 pi. And what's the frequency content of a DC? Just 0 hertz. And that's it. That's the frequency content. It's a 0 hertz. The Fourier transform of 1 over 2 pi is an impulse. Multiply this by 2 pi and 2 pi and you get this. The Fourier transform of 1 is 2 pi delta omega. Alright, this concludes today's lecture or the video. In next video, we will continue with some examples of famous function, especially modulation and so forth. Thank you.